Okay, so last unit we learned about objects that moved with constant velocities, right? We were learning about objects that were moving at the same speed the entire time. They never went faster or slower or changed directions. This unit will be talking about objects with changing velocities. And so objects with changing velocities are accelerating. So this is going to be kind of like our new vocabulary word. This is what we're going to be learning about this unit is acceleration. And so objects accelerate when a net force acts upon them. Now, you guys probably already know that a force is a push or a pull. We'll be learning more about net force later on in this unit. The important thing that you need to know is that stronger forces cause greater changes in velocity or accelerations. So the stronger the force, the faster an object will accelerate. The faster its velocity will change. Okay, and so because the velocities of accelerating objects are constant, the position versus time plots of accelerating objects are not linear. So up until now, when the position versus time plots that we've been looking at, they've consisted of straight lines or series of straight lines because the objects were moving at a constant speed. Now we're going to start learning about what happens when the speed or velocity of an object is changing as it is moving. And what we'll see is that the position versus time plots are curved. Right? That's kind of what we saw in yesterday's acceleration lab as the toy car accelerated down the ramp. Right? It had a curved position versus time plot. And so even though curved lines do not have a fixed slope, we can still estimate the average velocity of accelerating objects. So if you think about this, last unit we were using slope to tell how fast an object was going, right? The value of the slope told you how many meters that object was moving every second. Well, now the velocity is going to be changing, so we're not going to be able to find one velocity to describe the entire motion of the object. It'll be different at the beginning than it is at the end. So what we're going to be doing is determining the average velocity of our toy cars as they moved along. And you'll see it'll be very similar to how we calculated slope before. Okay, so even though curved lines do not have a fixed slope, we can still estimate the average velocity of accelerating objects over certain time or distance intervals using slope. So basically we're going to be able to say from this time to this time what the average velocity of an object is, or from this distance to this distance what the average velocity is. So we'll go through some examples of that in a second here. First, I just want to define average velocity. So average velocity is how fast the object is moving on average over a certain period of time in the acceleration. So, if you measured up all the times, between point A and point B and found the velocity at each time, this method for finding average velocity would tell you what the velocity was on average between point A and point B. And then graphically, it's just going to be the slope between 2 points on the position versus time curve. So even though it's a curved line, we're still able to mathematically calculate what the slope is. And we can use that to kind of like estimate what the average velocity is. So let's go through an example of that. Let's find the average velocity from 0 seconds to 4 seconds. And we can see the point at 0 seconds is at 0 seconds and 0 meters. The point at 4 seconds is at 4 seconds and 16 meters. And what we're going to do is we're going to find the slope between those 2 points. So we need to find the rise and the run, and that will help us find the slope of this line here. So let's see here, 16 meters minus 0, that's going to be to get the rise. So I'm going to take 16 meters minus 0 meters, and that'll get me 16 meters. And then to get the run, I'm going to do 4 seconds minus 0 seconds, and that will get me 4 seconds. So then for my work, I'm just going to do 16 meters divided by 4 seconds, that's 4 meters per second. And so then the answer is that the average velocity of the object was 4 meters per second over the first 4 seconds. So between 0 seconds and 4 seconds, the average velocity was 4 meters per second. Now, it wasn't moving that fast at the beginning, and it was certainly moving much faster than that at the end, but on average, from 0 to 4, the average velocity was 4 meters per second. Now, you can probably see that this line isn't a very good model for my slope here because, well, you can see that the blue line ends up kind of pretty far underneath the green line. Watch what happens though when we use the average velocity to just find the average velocity over the first second. What I think you're going to see is as we go from 0 seconds to 1 second, what we'll see is that green line going in between is a much better fit on that blue line. Look at it, it almost completely covers it up. There's just a little section down here where it dips underneath. And so because this section is straighter, we're going to get a better estimate out of the velocity by using the average velocity here. So over the first second here, if I want to find the average velocity, I'm going to do the same thing. I'm going to find the slope. So it's 1 meter up, right, because 1 minus 0 is 1. And it's 1 second over, right, because 1 minus 0 is 1. So my work is going to be rise over run equals 1 meter over 1 second. Well, that equals 1 meters per second. So the average velocity of the object was 1 meter per second over the first second. Not sure what's going on there. Okay. All right. So now let's find the average velocity from second 3 to second 4, from 3 seconds to 4 seconds. So we're going to go from here to here. So you can see these points are at 3 seconds and 9 meters and 4 seconds and 16 meters. Now I'm going to put the rise and the run. And again, you'll see that over this shorter section, the straight line estimate of the slope, it's a much better fit to the curve. So it's going to be, that tells us that it's going to be more accurate basically over this smaller interval compared to when we were finding the average velocity over the first 4 seconds. So let's see here, we need to figure out the rise. So that's going to be 16 minus 9, so that should be 7 meters. The run is going to be 4 seconds minus 3 seconds, so just 1 second. Then for my work, I'm going to take the rise over the run. So I'm going to do 7 meters over 1 second. That's going to equal 7 meters per second. So then my answer is that the average velocity was 7 meters per second over the last second. Okay, and so then my last example here is how much faster was the object traveling in the last second of the acceleration compared to the first second of the acceleration? Well, if I do 7 minus 1, that's going to get me to 6 meters per second. So the answer is the object was traveling 6 meters per second faster on the last second of the acceleration. Okay, so now what you're going to do is you're going to go to Pivot. You're going to open up the acceleration lab, and you're going to take a screenshot of your data table and your graph, and you're going to put them on this next page here. So you put the data table right here, and you put the graph right here. And then there's going to be some questions, and you're going to use the data table and the graph to find the average velocity of the toy car in the following questions. Like you'll figure out what the average velocity was, from the 0 meter mark to the 0.8 meter mark. You'll figure out the average velocity from 0 to 0.1, and then from 0.7 to 0.8. And then you'll tell me how much faster the car moved over the first 0.1 meters versus the last 0.1 meters. Let me know if you have any questions, as always.